आज हम बहुत ही बोरिंग टॉपिक पे इंटरेस्टिंग बात करने वाले हैं, the ionization chambers. So you must have heard about this term when we talk about various types of radiation detectors. It's a gas-filled detector, a detector in which gas is filled. You must have also heard about proportional counters and GM counters. Ionization chamber is a gas-filled detector as well, like all others. What will happen? You have a detector in which a gas is filled and a charged particle now passes through the gas. What will happen? Now you have a particular kind of gas which is filled in the detector, so the gaseous atoms or molecules are neutral. Now when a charged particle will enter this gas, it will either cause ionization or excitation of the gas molecules or atoms along its trajectory, along the path of that charged particle. It will either cause excitation or ionization of the neutral gas atoms or molecules. Now in case the gas molecule or atom is excited, as in the case of excitation, you do not get ion pairs. You only get ion pairs in ionization. So this excited gas atom or molecule can be used to derive the resulting signal, as in the case of gas scintillators. But here we are talking about ionization chambers and we need ion pairs. The actual interest here is in the ion pairs that are formed in the ionization, and it is these ion pairs which will eventually help you to derive your output signal. So you can say that the majority of the gas-filled detectors are based upon this principle, which use ion pairs as medium to produce the desired output signal, the output pulse. Let's keep the things simple. So this ionization chamber is the simplest of the gas-filled detectors. If you want to talk about the simplest of the gas-filled detectors, it's the ionization chamber. Now that you have ion pairs which are formed as a result of ionization of the neutral atoms or gas molecules, so you get ion. Next job is to collect these ion pairs, and how will you do that? You will apply a sufficient amount of electric field, and this imposition of electric field will enable these charge pairs, these ion pairs, to move towards their respective electrodes. This constitutes a current. The movement of charges constitutes current. Now it is to be noted that I am repeatedly using the term ion pairs. Ion pairs are collected in ionization chambers, while when you talk about semiconductor diode detectors, there I'll be using the term electron hole pairs. So right now we are talking about ion pairs. Now talking about the modes of operation, these ionization chambers, these are operated most commonly in current mode. They are used as DC devices. What are those? We'll be talking about in subsequent lectures. For the time being, there are two modes in which you can use it, current mode or the pulse mode. So ionization chambers involve these two modes of operation. Now talking about the GM counters, the other gas-filled detectors like GM counters and proportional counters, they are always used in pulse mode, unlike the ionization chamber, which is most commonly used in current mode. I'll put the links in the description box below. If you want to know about the pulse mode of operation, I have a video made for that as well. You can go back and check that. So now talking about the ionization process in gases. Now you know that you have a charged particle, the incident charged particle, and you have a detector in which you have some gas filled in it. Okay, now this charged particle, upon entering the gas, it will either cause excitation or ionization, as I already discussed earlier. So these are the two processes that can occur. The neutral gas atom or molecule can get excited, or it may result into formation of ion pairs. Now what is this ion pair that I'm talking about? If a charged radiation is passing through the gas, and as a result of this, this neutral atom, this neutral gas atom or molecule loses an electron. If it loses an electron as a result of this, it is said to have been ionized. So this will result in an electron and a resulting positive ion of the gas. So these two comprise of what we call ion pairs. So So these ion pairs will serve as a basic constituent of the electrical output signal, of the output electrical signal. So next thing would be to ask, how are these ion pairs formed? So one process is this direct ionization that we are talking about, that a charged particle enters, it ionizes the gas molecules or atoms and result in the formation of electron and the resulting positive ion pair of the gas. Now next thing can be secondary processes. Secondary processes like the delta rays, if they are involved. So what are these delta rays? Now you know that after ionization you will be getting an electron and a positive ion pair. Okay, so now if this electron after it has left its parent molecule or atom, this electron was a part of the gas, of the neutral gas atom or molecule prior to its ejection. After having left its parent atom, if this electron is having sufficient amount of kinetic energy, it can result in further ionization. Now this electron will cause further ionization of the gas and it will result in creation of new ion pairs. So you can say that instead of direct ionization, what is happening? Instead of the direct ionization by the incident radiation particle, it's now the electron which was produced in the primary ionization, it is now causing further ionization of the gas. Although it is to be noted that the range of these delta rays is much less as compared to the incident charge particle. So regardless of the detailed mechanisms that are involved in the formation of these ion pairs, it is the ion pairs that are of importance here. We are interested in the number of ion pairs that are formed. Now that we know that we are interested only in the ion pairs, so we need to know about how many ion pairs are formed. That is, we need to know about the total number of ion pairs that we'll be getting as a result of the interaction of this charged particle with the gas, with the neutral gas atom or molecules. So let's talk about this. So you know that ions will be produced only in the case of ionization. If ionization of the gaseous atom or a molecule occurs, only then you'll be getting ions. So the minimum amount of energy that the incident particle or radiation should possess is equal to the ionization energy. इससे कम होगी तो ionization नहीं होगा. So at least इतनी तो होनी ही चाहिए. So at least the particle should have this much amount of energy. So these are some common gases that are used in radiation detectors. These are common gases which can be used in radiation detectors, and the ionization energy for the least tightly bound electron shells, it ranges from 10 to 25 electron volt in these gases. तो जो भी gases radiation detectors में use होती हैं वो ये हैं. So the electron which is least tightly bound to the nucleus, it has a greater probability to be ejected as a result of ionization of the gas. It is the minimum amount of energy required for the electron to get ejected. So this means that 10 to 25 electron volt should be the energy range of the incident particle as well if you are using these gases in the radiation detectors. So E minimum that you are talking about, the minimum amount of energy should be 10 to 25 electron volt. Else you will not be getting ion pairs, and if you are not getting ion pairs, what the hell are we doing here? However, you know that there are other processes that are occurring. There are other processes that are occurring which do not lead to the formation of ion pairs. The process of excitation of the gas molecule, in which an electron may simply be elevated to a higher bound state within that neutral atom or a molecule, so that the atom or the molecule, the neutral gas atom or a molecule as a whole, is having energy greater than that of its ground state, but still that electron is in the bound state within that atom or a molecule. It's not able to come out of that trap. So you are not getting any free electron in this case. तो इंसिडेंट पार्टिकल की जो एनर्जी है, इंसिडेंट रेडिएशन की जो एनर्जी है, it is getting lost in processes which are leading to the formation of ion pairs, as well as processes which do not lead to the formation of ion pairs. अगर ये बात क्लियर है, if this point is clear and if you apply the law of conservation of energy, the total energy possessed by the incident particle should be equal to the energy lost by that particle. उतना ही होगा. And this energy loss comprises of processes creating ion pairs and processes not creating ion pairs. So the average energy lost by the incident particle per ion pair formed. Average energy lost by the incident particle per ion pair formed, इसको मैं define कर रही हूँ. I'm defining this quantity as W value. W value क्या होगी? This value will always be greater than the ionization energy. Why? Because it comprises of the energy lost. Energy loss should be equal to the actual energy that was present, and if the energy is going into processes, into two processes, minimum amount of energy was to create the ion pairs, but you know that there are other processes as well that are occurring. So जो energy loss होगा incident particle का per ion pair formed, that will always be greater than the ionization energy. So this W value will always be greater than the ionization energy. ये W value क्या है? W क्या? तो W value हमने define कर दिया average energy lost by the incident particle per ion pair formed. अब ये चीज़ क्या है? तो W value is a function of the gas species that is involved, the type of gas, then the radiation, the type of radiation that is involved, and third is the radiation energy. So it is a function of these three variables. लेकिन empirical observations कहती हैं it is not a strong function of any of these variables. It is dependent upon these but not strongly, very weakly. Strong function नहीं है. Empirical observations क्या हैं? Those that are experimentally observed based on some experiment. ठीक है, तो experimentally देखा गया है कि जो W है that is not a strong function of any of these. So for a given gas and type of radiation that enters it, the W value is constant irrespective of different radiation energy. So you can see a table in which you have some gases, their first ionization potential and the W value if the incident radiation is fast electron and for the case when the incident radiation is alpha particles. So W value is given in electron volt per ion pair formed. And you can see that for a given gas and the type of radiation, here the type of radiation is charged particulate radiation, as you can see. So these fast electrons and alpha particles fall into the category of charged particulate radiation. So ये इनकी type है. And for a particular gas, you can see that this is nearly constant. The W value is nearly constant for the type of radiation involved, irrespective of different radiation energies. Fast electrons and alpha particles can be of varying energies, but you can see that empirically it has been observed. If you fix a gas, the W value is nearly constant. So from the table also you can see that the first ionization potential, which is in electron volt, it is substantially less than the W value. So you can see that for these gases which are commonly used in radiation detectors, the W value is in the range of 25 to 35 electron volt per ion pair. So if this W value is constant for a particular gas and the type of radiation involved, what can you calculate? Say for example, if 33 electron volt is required to create one ion pair, so 1 MeV, which is equal to 10 raised to power 6 electron volts, will produce how many ion pairs? Roughly around 30,000 ion pairs. So if the incident particle is having 1 MeV of energy, it will produce around 30,000 ion pairs. So the W value for a given gas and the type of radiation involved, it is having a constant value. So W value is of great importance here because it enables you to find out the number of ion pairs, and these number of ion pairs is directly proportional to the incident energy, the actual energy deposited by the incident particle or radiation in the gas. You can calculate the number of ion pairs, and because of this proportionality, you can eventually calculate the energy of the incident radiation, the energy deposited by the incident radiation. So you can calculate the mean number of ion pairs produced by each incident particle or radiation. If you are talking about a single particle, this will be having some energy, let it be E. Incident particle किसी energy का होगा and you will be getting n number of ion pairs because of all the processes that are occurring. So this is leading to the formation of n ion pairs. तो end result ही आपको importance का है, the number of ion pairs that are produced, that is of interest, so you are able to calculate them. What about the fluctuations in this number? That is, now for the time being I'm fixing this radiation. For example, I'm talking about the alpha particle. Alpha particle is the incident radiation in this case, and it will be having some energy, say E, and which will result in the formation of n number of ion pairs. The next alpha particle that I'm talking about, that will be incident, that is also having an energy E, and what if this n is slightly different from the n calculated in the earlier case? Despite of the same amount of energy possessed by the incident alpha particle, what if my number of ion pairs produced is fluctuating? Likewise, if I have the same amount of energy associated with the incident particle, is it necessary that you will be getting the same number of ion pairs each time? हर बार अल्फा पार्टिकल उसी एनर्जी का आ रहा है, क्या ये ज़रूरी है कि आपको एंड में n नंबर ऑफ आयन पेयर्स ही मिलेंगे हर टाइम? n जो है वो वेरी कर सकता है, देयर विल बी फ्लक्चुएशन इन दिस n. So you know that the energy deposited by the incident radiation is directly proportional to the number of ion pairs formed, and this number of ion, this mean number of ion pairs formed is fluctuating. Now these number of ion pairs is directly proportional to the amplitude of the output pulse that you will be getting. The amplitude of the output pulse each time will be proportional to the number of ion pairs that are created by each interaction of the radiation particle with the gas molecules or atoms that you are talking about. And if there is a variation in the number of ion pairs produced for the monoenergetic incident radiation, this means that there will be variation in the pulse amplitude, the output pulse amplitude as well. So what you will be getting? A graph like this. So even if incident particles of identical energy are there, the output pulse amplitude will vary each time because the number of ion pairs produced are fluctuating. This plot is called a response function. Here dH is the differential pulse amplitude increment and dN by dH is the differential number of pulses observed with an amplitude within dH, which means that if you have 2 points, say H1 and H2 on the x-axis, the area under the curve between H1 and H2 will enable you to find out the number of pulses that have amplitude within H1 and H2. कायदे से what would have been the case, for the same amount of energy involved, you should be getting the same number of ion pairs. तो हमें एक डेल्टा फंक्शन मिल जाना चाहिए था, but actually we do not get a delta function. The graph that we will be getting is this. कोई peak centroid है H0, that is the value of the pulse amplitude. तो H0 amplitude के around आपको maximum number of pulses मिलेंगी. So if the total number of pulses recorded is N0, these pulses will have different amplitudes even if the incident particles had identical energy, and the resulting distribution is Gaussian with standard deviation sigma about the peak centroid H0, which is the mean value. So what will be the full width at half maximum? The maximum value, the maximum Y value you know is this. The Y value corresponding to the peak centroid. Now to calculate full width at half maximum, you just see what is exactly half of this maximum Y value. And corresponding to this Y by 2, you will be getting two values of the pulse amplitude, say H1 and H2. And this full width at half maximum is nothing but the difference between this H1 and H2, which will be in volts, and the units will be same as that of the pulse amplitude. So you define the resolution of such a graph as full width at half maximum divided by the peak centroid. For the Gaussian shaped peak, you have this value. So you have this relation for Gaussian peaks. For the case of full width at half maximum, that is, it is 2.35 sigma. Simply putting the values of full width at half maximum and the peak centroid, you will be getting this resolution. So for calculating the resolution, all you need is the location of this peak centroid the value of this peak centroid and this standard deviation, which is sigma. So if you want to know about the energy resolution, we have a video made for that as well. You can see the link in the description box below. Check it out. So what is the end result? For the incident particles of the same energy E, you are getting a sigma. You are getting some standard deviation in the response function. If you are getting a standard deviation sigma, what does that mean? The sigma is related to the energy resolution, the expression that we just saw. Is sigma se kya hoga? This value of sigma will actually limit the value of this resolution. Resolution that can be achieved in any radiation detector. And what is this resolution that I am talking about? Go back and check my previous videos. If you don't watch my videos, how will you understand my lectures? Go back and watch my previous videos. Go back and watch all my previous videos. So the sigma, this standard deviation, this limits the resolution that can be achieved in any radiation detector. And what is this sigma? It is nothing but a measure of fluctuation. Sigma indicates fluctuations. Fluctuations kiski? In the mean number of ion pairs that were produced. Now let us simplify the things. All you have to do is you have to assume a simple model wherein the formation of each ion pair is considered as a Poisson process, which means that the formation of ion pairs, this will be following a Poisson distribution. Now this Poisson distribution will be having some mean. Now अगर ये Poisson distribution है तो इसका कोई mean होगा, इसका कोई average होगा. तो talking about the average number of ion pairs that are getting formed, let it be say number say n. ये कोई number है, ठीक है. उसके बाद अब इस Poisson distribution का कोई standard deviation, इसका कोई standard deviation होगा. Standard deviation क्या होगा? Root of mean. For the Poisson distribution, you know that standard deviation is nothing but the square root of this mean. So sigma will be under root n. And this is nothing but the fluctuation in this mean number of ion pairs produced. So if you believe in this simplified model, it will result in sigma, which is equal to the fluctuations as observed in the Poisson distribution, which will be under root n. But this is life and reality इसके आसपास नहीं है. Reality is that in radiation detectors, this observed fluctuations is comparatively less, is significantly less as compared to this sigma. So observed fluctuations in radiation detectors is less than that predicted by the simplified model. जो सिग्मा है, जो सिग्मा आपका स्क्वायर रूट n आया है, जो ये ऑब्जर्व्ड सिग्मा है, इसकी वैल्यू रूट n से कम आती है. तो रूट n से कम आती है मतलब कोई फैक्टर आपके इसके साथ मल्टीप्लाई होना चाहिए जो इस रूट n को कम कर रहा है. इनके साथ कोई ऐसा फैक्टर मल्टीप्लाई हो जाए जो कि इसको कम कर दे, वो होगी आपकी ऑब्जर्व्ड फ्लक्चुएशंस. तो देखा कुछ और गया है, आपका मॉडल कुछ और कह रहा है. अब सिग्मा मैं बोल रही हूँ स्टैंडर्ड डेविएशन. अगर स्टैंडर्ड डेविएशन पता है तो वेरिएंस तो पता ही होगा. वेरिएंस इज स्क्वायर ऑफ दिस स्टैंडर्ड डेविएशन, सिग्मा स्क्वायर. अब मुझे यहाँ पे एक सोफिस्टिकेटेड सी क्वांटिटी डिफाइन करनी होगी, द फैनो फैक्टर. फैनो फैक्टर क्या कहेगा? ये जो डिस्क्रिपेंसी आ रही है सिग्मा की, ये अब आपने कहा है ये कम होती है, जो आपने बताई है सिग्मा उससे कम होना चाहिए. तो ये डिस्क्रिपेंसी सॉल्व करने के लिए कौन आएगा? ये फैनो फैक्टर आएगा. तो फैनो फैक्टर क्या है? तो दिस फैनो फैक्टर इज नथिंग बट द एक्सपेरिमेंटली ऑब्जर्व्ड वेरिएंस इन n डिवाइडेड बाय द पॉइजन ऑब्जर्व्ड वेरिएंस. आयनाइजेशन चैम्बर के बारे में बात कर रहे हैं. ये गैस फील्ड डिटेक्टर है एंड फॉर गैसेस दिस f इज empirically observed to be less than 1. एक्सपेरिमेंट्स में देखा गया है कि f की वैल्यू लेस देन 1 है. अब अगर f लेस देन 1 है तो आ गया ना ये ऑब्जर्व्ड आपका सिग्मा लाइन पे आ गया. तो इससे क्या हुआ? चीज़ें हल हो गई. जो आपकी ऑब्जर्व्ड वेरिएंस है वो कम आ गई एज दैट प्रेडिक्टेड बाय द पॉइजन डिस्ट्रीब्यूशन, पॉइजन स्टैटिस्टिक्स अलोन. ऑब्जर्व्ड फ्लक्चुएशन लेस देन पॉइजन फ्लक्चुएशंस आ गया. अब सोचो कि इफ द एंटायर एनर्जी ऑफ द इंसिडेंट रेडिएशन वाज ऑलवेज कन्वर्टेड इनटू द फॉर्मेशन ऑफ आयन पेयर्स, जो एनर्जी थी इंसिडेंट पार्टिकल की उसे लूज होना है किसी प्रोसेस में, विच मे रिजल्ट इन फॉर्मेशन ऑफ आयन पेयर्स और नॉट. अब अगर मैं कह रही हूँ कि वो एनर्जी लॉस जो हो रहा है उससे सब आयन पेयर्स ही बन रहे हैं हर टाइम, तो उससे क्या होता? अगर एक इंसिडेंट रेडिएशन है किसी पर्टिकुलर एनर्जी की और हमेशा एनर्जी लॉस आयन पेयर्स में ही हो रहा है, आयन पेयर्स के फॉर्मेशन में ही हो रहा है, तो हर टाइम, नोट इट, हर टाइम सेम नंबर ऑफ आयन पेयर्स ही बनते for the same incident particle for the same incident radiation of same energy. उसी एनर्जी की रेडिएशन अगर बार बार आ रही है, वो हमेशा आयनाइजेशन ही कर रही है और कोई और प्रोसेस नहीं हो रहा, कोई और प्रोसेस में वो एनर्जी नहीं जा रही, सिर्फ और सिर्फ आयन पेयर्स ही प्रोड्यूस हो रहे हैं। और हर टाइम वो इंसिडेंट पार्टिकल सेम अमाउंट ऑफ एनर्जी के साथ आ रहा है, तो हर टाइम सेम नंबर ऑफ आयन पेयर्स ही प्रोड्यूस होने चाहिए थे। इस एन में कोई फ्लक्चुएशन नहीं होनी चाहिए थी। तो जो आपने रिस्पॉन्स फंक्शन पहले पढ़ा वो बेकार था। वो इस केस में क्या होता, दैट विल बी अ सिंपल डेल्टा फंक्शन। तो एक एनर्जी का इंसिडेंट पार्टिकल आया, उसने कुछ फिक्स नंबर ऑफ आयन पेयर्स प्रोड्यूस कर दिए और कॉरस्पॉन्डिंग टू दैट फिक्स नंबर ऑफ आयन पेयर्स एक फिक्स्ड आपको एम्पलीट्यूड की आउटपुट पल्स मिलती हर टाइम। एक फिक्स्ड एम्पलीट्यूड से H0 जो कि पीक सेंट्रॉइड था आपके पिछले ग्राफ में, एक पर्टिकुलर एम्पलीट्यूड की पल्स मिल गई, फिर नेक्स्ट टाइम भी उसी एनर्जी का आ रहा है, फिर आपको उसी पर्टिकुलर एम्पलीट्यूड की मिलेगी। तो वो एम्पलीट्यूड जो है उसमें वेरिएशन नहीं आएगी। उस एम्पलीट्यूड में पल्स एम्पलीट्यूड हर टाइम जो होगा वो उसी पे ही ओवरलैप करता रहेगा हर एक इवेंट के लिए। तो आपको क्या मिलेगा, एक मैथमेटिकल डेल्टा फंक्शन मिलेगा जिसमें आपको सिग्मा नहीं आएगा। सिग्मा विल बी ज़ीरो, सिग्मा जो ऑब्जर्व्ड होगा वो दैट विल बी ज़ीरो। तो ऑब्जर्व्ड फ्लक्चुएशन विल बी ज़ीरो। फ्लक्चुएशन किस लिए आती है, स्टैंडर्ड डेविएशन जब आप बात करते हैं, तो इसकी कोई स्टैंडर्ड डेविएशन नहीं, तो इस ग्राफ की कोई स्टैंडर्ड डेविएशन नहीं और कोई फ्लक्चुएशन नहीं, ठीक है। तो ऑब्जर्व्ड फ्लक्चुएशन ज़ीरो हो गई, विच मीन्स दैट इन दिस केस फैनो फैक्टर ही ज़ीरो हो गया। और फैनो फैक्टर आया क्यों था, फैनो फैक्टर इसीलिए आया था क्योंकि जो आपका पॉइजन प्रेडिक्टेड जो प्रोसेस है उसमें जो फ्लक्चुएशन आई थी और जो आपकी एक्चुअल में देखी गई थी फ्लक्चुएशंस, उसमें कुछ डिस्क्रिपेंसी थी। वो जो एक्सपेरिमेंट रिजल्ट आपका थ्योरी से मैच नहीं कर रहा था। अब जब एक्चुअल में हम फ्लक्चुएशंस ऑब्जर्व ही नहीं कर रहे तो हम फैनो फैक्टर के बारे में बात क्यों करें। तो डिड यू ऑब्जर्व ये फैनो फैक्टर कर क्या रहा है, व्हाट इज दिस फैनो फैक्टर डूइंग, व्हाट इज दिस फैनो फैक्टर इंडिकेटिंग टूवर्ड्स, इट इज इंडिकेटिंग टूवर्ड्स द पार्टीशनिंग स्टैटिस्टिक्स, partition of energy. If this energy of the incident radiation entirely goes into the formation of ion pairs only, अगर यही होता, पार्टीशन ऑफ एनर्जी नहीं होता। पार्टीशन ऑफ एनर्जी मतलब कि जो आपके लॉस हो रहे हैं वो कभी आयन पेयर्स में गए या किसी दूसरे में गए। अगर इस तरह का पार्टीशन नहीं है तो आपको पता है एक मैथमेटिकल डेल्टा फंक्शन आया था आपका, फ्लक्चुएशन ऑब्जर्व्ड ज़ीरो आ गई थी, तो फैनो फैक्टर की कोई बात नहीं की। फैनो फैक्टर कब आया, व्हेन वी आर टॉकिंग अबाउट अदर प्रोसेसेस दैट आर आल्सो अकरिंग along with the processes that are resulting in the formation of ion pairs. So Fano factor indicates towards some sort of a partitioning statistics. That is, some amount of particle energy is lost in processes which are not resulting in the formation of ion pairs. You remember we talked about excitation process. So this incident particle energy goes into the formation of ion pairs as well as in exciting the neutral atoms or neutral molecules of the gas. And this excitation process will not give you any ion pair. तो फैनो फैक्टर को एग्जिस्टेंस में कौन ला रहा है, फैनो फैक्टर्स को एग्जिस्टेंस में कौन ला रहा है, कुछ ऐसे प्रोसेसेस जिसमें कि आयन पेयर्स प्रोड्यूस नहीं हो रहे लेकिन इंसिडेंट पार्टिकल का कुछ अमाउंट ऑफ एनर्जी उनकी तरफ जा रहा है, उन प्रोसेसेस को होने में जा रहा है। एक तो होगी टोटल एनर्जी जो कि इंसिडेंट पार्टिकल के पास है, out of that the amount of energy, the amount of radiation energy that is going in processes, that is lost in processes which do not lead to the formation of ion pairs, energy lost in processes which do not lead to the formation of ion pairs. तो ये जो फैक्टर है अगर ये न्यूमरेटर में आ जाए डिवाइडेड बाय द टोटल अमाउंट ऑफ इंसिडेंट एनर्जी, ये कोई फ्रैक्शन आ गया, इसके बारे में आई थिंक ये फैनो फैक्टर बता रहा है, इंडिकेट कर रहा है। नाउ इफ नो एनर्जी इज लॉस्ट इन प्रोसेसेस व्हिच लीड टू द फॉर्मेशन ऑफ आयन पेयर्स, दिस फैनो फैक्टर विल बी जीरो बिकॉज एनर्जी लॉस इन दिस न्यूमरेटर जीरो हो गया, फैनो फैक्टर जीरो हो गया। सो इफ नो एनर्जी इज बीइंग लॉस्ट इन प्रोसेसेस दैट डू नॉट क्रिएट आयन पेयर्स, तो इस तरह के अगर प्रोसेस में नहीं जा रही तो इसका मतलब क्या है कि सारी एनर्जी उन प्रोसेसेस में जा रही है दैट क्रिएट आयन पेयर्स। तो दैट मीन्स दैट उस केस में क्या हो जाएगा, फैनो फैक्टर ज़ीरो हो जाएगा। और जो डायग्राम आपको मिलेगा रिस्पॉन्स फंक्शन का, दैट विल आइडियली अप्रोच अ डेल्टा फंक्शन, जो होगा आपका डेल्टा फंक्शन। तो उस केस में फैनो फैक्टर 0 हो गया आपका, बिकॉज एनर्जी जो ये न्यूमरेटर है आपका ये 0 हो गया। दिस फैनो फैक्टर लेस देन 1 इंडिकेट्स दैट out of the total incident energy, some amount of energy goes in processes that do not create ion pairs. But it is to be noted that Fano factor equal to 1 doesn't mean that all the energy is going in processes which do not lead to formation of ion pairs. And what the hell are we doing here? अब अगर ion pairs ही नहीं मिल रहे आपको तो what the hell are we doing here? अगर ion pairs ही नहीं मिल रहे, why at all are we talking about the ionization chambers wherein you need ion pairs? तो Fano factor equal to 1 actually means that कि जो आपकी डिटेक्टर रेजोल्यूशन है, जो डिटेक्टर की रेजोल्यूशन है, that is equal to the expression that you will be getting for the resolution when we assume the simplified model to be acting, wherein the creation of each ion pair is governed by Poisson statistics. तो अगर आपकी फैनो फैक्टर, तो आपका अगर फैनो फैक्टर 1 है, दिस मीन्स दैट जो आपका डिटेक्टर है, जिस डिटेक्टर के रेजोल्यूशन के बारे में आप बात कर रहे हैं, उसमें आयन पेयर्स के जो फॉर्मेशन का प्रोसेस है, दैट इज गवर्न्ड प्योरली बाय पॉइजन स्टैटिस्टिक्स अलोन. Fano factor less than 1 on the other hand indicates the departure of the observed statistical fluctuations in the number of charge carriers from pure Poisson statistics. तो फैनो फैक्टर लेस देन 1 क्या कर रहा है, जो आपकी ऑब्जर्व्ड स्टैंडर्ड डेविएशन है उसको कम कर रहा है. तो अगर आप पॉइजन स्टैटिस्टिक्स फॉलो कर रहे हैं तो जो उसका स्टैंडर्ड डेविएशन होगा का एक तो वो है. अब ये जो ऑब्जर्व्ड स्टैंडर्ड डेविएशन है, जब आप फैनो फैक्टर को अकाउंट में लेंगे तो दिस सिग्मा ऑब्जर्व्ड विल बी लेस देन दैट ऑब्जर्व्ड बाय द पॉइजन स्टैटिस्टिक्स अलोन. तो प्योर पॉइजन स्टैटिस्टिक्स का सिग्मा अलग है और फैनो फैक्टर को इंक्लूड करके जो फ्लक्चुएशंस आ रही हैं, जो स्टैंडर्ड डेविएशन है, वो कम होंगी. तो ये जो आपका गॉसियन शेप्ड पीक है ये नैरो हो जाएगी एंड यू विल बी गेटिंग मोर नंबर ऑफ पल्सेस अराउंड दिस मीन वैल्यू. सो इन गैसेस दैट आर जनरली यूज्ड in the radiation detectors, this Fano factor is generally less than 1, which means nothing but that the observed fluctuations will be smaller than that governed by Poisson statistics, pure Poisson statistics alone. So at this point, another information that I would like to share is this Fano factor has significance only when the detector is operated in pulse mode, which means that when we will be talking about proportional counters and GM counters, which are generally operated in pulse mode only, there this Fano factor will be having much more importance. Guys, that was all for today. I hope you liked my video. If you do not forget to give it a big thumbs up. Do subscribe to my channel and press the bell icon so that you get a notification whenever I post a video on YouTube. Go back and check my previous videos if you have any doubts in the topics that I have discussed in this video. I'll be back with my next video. Till that time, do not forget to take really good care of yourselves. Bye bye.